Good evening, everyone. I am Amit Gupta. I am here to present the paper titled A Review of Control Strategies for Operation of Distributed Resource Under Grid Fault. The author of the paper is myself and Dr. P.C. Sekhar. Motivated by the concerns of the environment, energy shortage, and reliabilities, there have been seen a huge development in the field of DGs integrating with the grid, and we can also see the DGs. The major source of the DGs are basically most of the renewable sources. And before that, in earlier days, non-renewable sources are uses, but due to the environment concern, they are shifting to the renewable based sources. And in the histogram plot also, we can see there was a development in the installed capacity of wind and solar in the recent years. And but we can observe that the renewable source which are integrating with the grid, they are integrated by converters, which are basically made of power electronics converters, and these power electronic converters are very sensitive to current. So it can only tolerate to 1.1 to 2 PO of the fault current. So a control strategy need to be developed so that it will limit the fault current which are passing through the converters and protect our converters. Whatever the strategies mostly derived, it is basically based on the balance fault. But a few papers are there who talked about the unbalanced fault in the systems. So the author has reviewed those strategies who talk about the unbalanced fault in the systems. So in this paper we have basically divide the strategies into three parts based on the nature of the waveform of the current. The first one is non-sinusoidal current. In these two strategies we have discussed. First one is instantaneous controlled positive sequence strategies, and second is instantaneous active and reactive power theory. The next is sinusoidal current but unbalanced in the nature. So in this also we have two strategies: average active and reactive control and positive and negative sequence control. And the last is sinusoidal but balanced current. In this we discuss balanced positive sequence control strategies. So according to the instantaneous power theory, the instantaneous active power and reactive power can be given by the combination of voltage and current. The dot product will give rise to the active power component, and the cross product will give rise to the reactive power component. And we also know that at the time of unbalanced fault, the voltage and current will consist of positive sequence component, negative sequence component, and zero sequence component. But in our studies, we are considering three-phase system, so the zero sequence component will not present. So only positive sequence and negative sequence component is present. And in the power equation, we also seen that the combination of same sequence component will give rise to the average instantaneous active power component, and the combination of different sequence component will give rise to the oscillation in the power. Similarly, in the both the power, active and reactive power. So first strategy we studies about the instantaneous active reactive power control, which are focused on instantaneous values, and here the current reference can be given by the by the multiplication of instantaneous conductance with the voltage, and the reactive power component current component will give the instantaneous susceptance with the conjugate of the voltage component, and the value of this conductance and susceptance can be given uh, by these equations. But after putting the values of G and B, we got active component of the current and the reactive component of current. But it can be seen that this V square term, it will consist of a 2 omega frequency, which will create a non-sinusoidal component due to the presence of 2 omega terms in the current. So the next strategy we study about the instantaneous control positive sequence control theory. In this strategy also, it due to the presence of positive and negative sequence component, combination of positive and negative sequence component, it will again give rise to 2 omega terms. So again it will produce a non-sinusoidal current. But this method was basically focus from the positive component of the current vectors. Then The third strategy was the average active reactive power control, and this strategy is similar to the ARC, but instead of instantaneous value, it was focused on the average value of the instantaneous susceptance conductance, and this average value can be derived in one grid cycle by using this. So after putting the values, these are the current reference equation case for the active and reactive component. But after these values, when we put in the power equations, we can see here again v square will term, which will create a oscillation in the power component. So after that, we study the next strategy, that is balance positive sequence control strategies. This strategy basically focus on only the positive component and neglecting the negative sequence component of the voltage. In this way, we obtain the active component of the current waveform, which was totally dependent on the positive sequence component. Similarly, the reactive part of the current is also dependent on the positive sequence. But in the system, the voltage will having both positive and negative component happening. So the interaction of negative component of voltage with the positive component of the current will give rise again in the oscillation. So in this strategies, the oscillating term in the active and reactive power, both the power, it cannot be removed. Now the last strategy is the positive and negative sequence control. In this stage, the active power which is generated is free from the oscillation when we are operating in the unity power factors. And in this strategy, all the both the positive and negative sequence component is taken, and the current which are generating is consists of both positive and negative sequence control. Now, a comparative studies has been done for all studies, and these are the table which are formed, which are showing the characteristics of the discussed strategies. In this, we can see the IARC and ICPS having the two megaterms, which is creating the non-sinusoidal nature of the current waveform. And in PNSC, in the PNSC, due to the presence due to the subtraction of positive sequence component and negative sequence voltage in the denominator, it if the positive sequence component is equal to the negative sequence component, the denominator will become zero, thus the quantity become infinite. So this strategy is not valued when the positive sequence component is equal to the negative sequence strategy. And even though BPSC is producing the sinusoidal imbalance current due to the presence of negative sequence component of the voltage and the interaction of positive sequence component of current with the negative sequence current component of the voltage, it gives rise oscillation in both active and reactive power. So and this is the simulation studies we done for all the five strategies. Here we use SOGI controller to decompose the component of the voltage, and we use hysteresis control to generate the PWM for the switches. And these are the parameters we have taken for designing our systems. So this is the simulation result, and here this is the result showing the DG feeding current to the grid at the time of unbalanced fault. Here we can observe the IRC and ICPS consist of non-sinusoidal current, and BPSC producing the sinusoidal current and balance in nature. But and ARC and PNSC, even though they are producing sinusoidal, but they are in unbalanced condition. Now the next result is the waveform of active power and reactive power, which are flowing from the DGs and delivering to the grid. Here we can observe IARC having zero oscillation in both active and reactive power, and BPSC having oscillation in both active and reactive power, which cannot be nullified due to the presence of negative sequence of the voltage and positive sequence of the current. And here we can also observe the ARC having the higher oscillation compared to other strategies. So coming to the conclusion, here we have discussed the we have reviewed the five control strategies which are used under the unbalanced fault. Basically, we here we consider only the LG fault, which is because it is the most common fault in the power systems. And here we have also seen the effect of negative component system on the integration of DG with the grid. And these are the references. Thank you.